Welcome, data engineers and architects. Today, we are diving deep into one of the most powerful optimization features in Apache Spark, dynamic resource allocation. Let's get started and transform how you manage cluster resources. Let's begin by defining what dynamic resource allocation, or DRA, actually is. When you run a Spark job traditionally, you ask for a fixed number of executors. If you ask for 50, you get 50, and you hold on to them for the entire lifecycle of the application even if they are sitting idle. DRA completely flips this paradigm. As noted in our first bullet, it dynamically adjusts executor count based on your real-time workload. If your job experiences a sudden burst of data, DRA requests more executors. Once the heavy lifting is done and those executors sit idle, DRA gracefully releases them back to the cluster manager. This elasticity is absolutely critical when you are operating in multi-tenant environments like YRN or Kubernetes, as it ensures you are only using what you truly need. Take a look at this diagram comparing static and dynamic approaches. On the top path, a static application locks in fixed resources, which inevitably leads to wasted capacity during idle periods. On the bottom path, we see the dynamic approach. The application monitors its own state. When it detects high load, it scales up the executors to process tasks in parallel. Conversely, when it detects low load, it scales down, returning those precious resources to the cluster. It's a simple, elegant loop of continuous optimization. Now that we know what it is, let's talk about why you must use it. The biggest problem in large-scale data processing is resource hoarding. Developers often over-provision resources, requesting maximum executors just in case they hit a heavy data skew. With DRA, as bullet point 1 highlights, resource hoarding is eliminated. But why does this matter to the business? Cost efficiency. In a cloud environment like AWS or Azure, idle executors cost real money. By releasing them, you slash your compute bill. Furthermore, from a platform perspective, DRA improves overall cluster throughput. When your job releases an executor, another pending job can immediately grab it. Finally, DRA natively adapts to skewed or bursty workloads, scaling up only when that massive shuffle stage actually hits. Here is a breakdown of the core benefits of DRA. At the top, we have our central question: why DRA? It branches into 3 pillars: cost savings, better throughput, and multi-tenant fairness. Under cost savings, we clearly see that you pay only for active compute, crucial for modern cloud architectures. Under better throughput, releasing resources leads to shorter queue times for everyone else. And under fairness, it actively prevents greedy jobs from starving the cluster. It is a win-win-win scenario for data engineers and platform admins alike. Let's dive into the mechanics. How does Spark know when to scale? It relies on 2 main policies: the request policy and the remove policy. For the request policy, Spark monitors the task scheduler. If there are pending tasks waiting because no executors are available and they wait past a specific timeout, Spark requests more executors. But here is the brilliant part: it scales exponentially. It doesn't just ask for 100 executors at once. It asks for 1, then 2, then 4, then 8. This exponential scaling prevents the cluster manager from being overwhelmed. On the flip side, the remove policy monitors idle time. If an executor finishes its tasks and sits completely idle for a defined period, Spark politely asks the cluster manager to terminate it. This continuous loop ensures your job perfectly tracks its actual resource needs. This state diagram perfectly visualizes the continuous heartbeat of dynamic resource allocation. From the initial state, Spark enters a monitoring phase. If it detects a task backlog timeout, it shifts to requesting and scales exponentially, adding executors in multiples of 2, before returning to monitoring. If it detects that an executor has hit the idle timeout, it shifts to the removing state, gracefully killing the executor, and returns to monitoring. This lifecycle continues seamlessly until the Spark job finishes. Now we reach a critical architectural deep dive: the external shuffle service, or ESS. Imagine this scenario: an executor finishes its map tasks, writes out shuffle data, and becomes idle. DRA says, "Great, let's kill it to save money." But wait, the next stage needs that shuffle data. If the executor dies, the data dies with it, forcing Spark to recompute everything. This completely defeats the purpose of DRA. Enter the external shuffle service. ESS is an independent daemon running on the worker node, completely separate from the Spark executor. Executors write their shuffle files to the ESS. Because the data is now decoupled from the executor's JVM, Spark can safely terminate the idle executor. When the next stage begins, the new executors simply fetch the data from the SS. It is a mandatory requirement for DRA. This diagram illustrates the magic of the external shuffle service. On the top left, Executor 1 finishes its map tasks and writes its shuffle data straight into the external shuffle service, highlighted in pink. Because the data safely resides in the SS, Executor 1 can be terminated by DRA, falling into the void without any negative impact. Later, Executor 2 spins up for the reduced tasks and successfully fetches the required data directly from the SS. The computation continues without a hitch. Let's look at how you actually turn this on in your Spark configurations. To enable DRA, you must set spark.dynamicallocation.enabled to true. But as we just discussed, you must also set spark.shuffle.service.enabled to true. If you forget the shuffle service, your job will fail or suffer severe performance degradation. Next, you must set your boundaries. Spark.dynamicallocation.min executors determines your floor. It defaults to 0, meaning your job can scale down to just the driver. Spark.dynamicallocation.max executors sets the ceiling. Be very careful here, the default is infinity. You should always cap this to prevent a single buggy job from eating the entire cluster. Finally, you can use initial executors to give your job a running start, avoiding the delay of waiting for the exponential scaling to kick in. This flow shows the mandatory and recommended configurations for DRA. From your Spark configs, you must branch out and explicitly enable both dynamic allocation and the shuffle service. Then, you move to setting your boundaries. I always recommend explicitly setting min executors, say to 2, so the application always has a baseline footprint, and capping max executors, say at 50, to ensure you are playing nicely with other tenants on the cluster. For senior engineers, the default settings aren't always enough. Let's deep dive into the timeout configurations. Executor idle timeout defaults to 60 seconds. If your tasks have large gaps between them, you might want to increase this to avoid thrashing, constantly killing and spinning up executors. Cached executor idle timeout is critical. It defaults to infinity. If an executor is caching an RDD or data frame in memory, Spark won't kill it because reading from disk again would be too expensive. If you change this, be aware of the performance penalty. Finally, we have the backlog timeouts. Scheduler backlog timeout is how long Spark waits before making its very first request for new executors, usually 1 second. Sustained scheduler backlog timeout governs the time between the subsequent exponential requests. Here we categorize the advanced timeouts into scale down and scale up operations. Under scale down, we see the standard idle timeout at 60 seconds and the cached idle timeout safely set to infinity to protect in-memory data. Under scale up, we see the aggressive 1-second backlog timeouts. Spark is designed to scale up very aggressively when work is waiting, but scale down conservatively to ensure it doesn't accidentally kill an executor it might need a few seconds later. Let's apply this to a real-world use case that is incredibly common, a multi-tenant data lake running on a shared cluster. Imagine you have heavy scheduled ETL pipelines running overnight and a team of data scientists running ad hoc queries during the day. If you use static allocation, you have to split the cluster, say 50/50ths. At night, the ETL jobs are starved for resources, while the data science queue sits totally empty and wasted. With dynamic resource allocation, the cluster breathes. At 2 a.m., the ETL jobs burst, scaling up to consume 90% of the cluster, finishing in record time. As they finish, they scale down to 0. By 9 a.m., data scientists log in. When they execute a complex machine learning query, their notebooks dynamically scale up using all that freshly freed capacity. DRA ensures 100% utilization of your infrastructure investment. Look at the resource flow in the shared cluster environment. At night, the ETL jobs trigger and DRA scales them to 90% utilization. Once finished, DRA elegantly scales them down to 0. Notice the dotted line. The exact resources freed by the ETL jobs are seamlessly handed over to the data science workloads during the day. This dynamic swapping of compute power is the ultimate goal of modern data architecture, providing agility and massive cost savings. To wrap up, let's cover limitations and best practices. First, DRA does not work with Spark streaming, specifically dstreams, because streaming data is continuous. Executors would constantly flap up and down, destroying latency. Second, never leave max executors at infinity. I've seen single poorly written queries take down entire production clusters because they scaled indefinitely. Set a hard limit. Third, keep an eye on garbage collection. DRA can sometimes mask bad memory configurations because it just throws more executors at the problem. Finally, always combine DRA with proper partition tuning to ensure your tasks are evenly distributed. That brings us to the end of our masterclass on dynamic resource allocation. To truly master Apache Spark, invite yourself to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. See you there. Our final diagram distills these best practices into a simple checklist. Always remember to disable DRA for streaming workloads, monitor your garbage collection, and tune your partitions. Most importantly, highlighted in orange, cap your max executors. Thank you for joining this deep dive. Be sure to like, subscribe, and visit quicktechie.com for premium certification prep, full ebooks, audiobooks, complete training modules, and expert interview guides. Happy optimizing!